the name of it online, and let me just pull it up right now.
So how long have you been teaching? Because my mom said that you were teaching calculus. Is that right?
Yeah, I actually taught, I actually have my master's degree in math, so I'm still teaching at Fisher, but my expertise is actually in mathematics. I taught at NEQA for several years and got even my master's degree in mathematics. So it's something I enjoy doing still. And in fact, I enjoy it more now that I'm not teaching it. Makes it a little bit more, you know, I have more energy to do it. If I was teaching it all the time, I don't think I'd want to tutor it on, you know, after school and on the weekends. But it's you know, it's fun, and it, you know, helps put my own kids through college. So that's why I still do it. And I do enjoy it. It's fun to do. So anyway, so here we go. We've got, you want what from number 11, I assume?
Yes.
Okay. So do you remember the derivative? Do you have the notes on what the derivative, if f of x is e to the u, let's say, do you remember what the derivative of x is?
Is it UE or?
It's actually e to the u times the derivative of u with respect to x.
Gotcha.
Now, different textbooks and different teachers use different notation. So can you tell me what notation you use for that? So I don't want to confuse you.
For the derivative?
Yeah, for the derivative of e to the u, for example.
We just started with that, but I'm not so sure because I haven't been doing well because my teacher isn't really teaching.
Okay.
Yeah, it's that's why I've been having troubles with the class, and frankly I don't even know where we are in class.
Okay, so do you have notes from the class or no? No. Okay.
No.
She doesn't. He or she? Is it a he or she?
It's a she. She doesn't give us notes, and I'm like, okay.
And so is there like a textbook that you use that you can refer to?
We have our textbook, but the textbook they pick is not the best.
Okay.
So it's kind of like learning everything from the base right now.
Okay. I'll just do it then the way that I'm used to seeing it.
Okay.
So the derivative, so this is how I'll show this. Whoops, didn't want to clear that. This is how I'll show you. If I want to take the derivative, let's call this y. I don't know. Sometimes you can call it f of x, or sometimes you can just say y equals e to the u. Then the derivative of y with respect to x. Notice that this function is not in terms of x. You see how this function here is in terms of u?
Mm-hmm.
So u is actually a function of x. In other words, u has x in it. U is like, well, like in our examples here. Number 12, u would be 2 to the x. Number 14, u would be negative 3x. Number 19, u is 2x. You see what I'm talking about?
Yes.
So when the derivative of e to the x with respect to x is just e to the x. That's the derivative of e to the x. It actually is itself. Okay, that's an important thing to understand. But if you're trying to find the derivative of something that isn't just e to the x, it's something e to the something else that has to do with the x, then you have to take the derivative of that exponent as well. So the derivative, so first of all, do you understand this notation that I'm using here? dy
yes.
dx. Do you understand that? This literally means the derivative of y with respect to x. That's what this means down here. So the derivative of y with respect to x is going to be equal to e to the u. Notice I'm bringing this entire thing back, and then I'm going to multiply that by the derivative of u with respect to x. That's the
Okay.
that's the answer, or that's the way you do it. So let me do some of these problems for you. Number 11. So number 11, it would be if y equals e to the 3x, then y, the derivative of y, which also can be written as that, right? Or here, let me be consistent. dy dx is equal to e to the 3x times 3, because 3 is the derivative of 3x. That make sense?
Yes.
So number 12, y equals e to the 2x, the derivative, now I'm going to write it differently, because sometimes you'll see it written like this: y prime with respect to x is just 2 e to the x. Notice now I'm writing the 2 in front, because that's really what looks better. It would have looked better if I wrote the 3 in front. 3 e to the 3x. That's the right way to write that.
Okay.
Okay, so there's the answer for number 1 or 11. There's the answer for number 12. Number 13. So if y equals 5e to the negative 2x, what is the derivative? What's y prime equal?
It would be the negative 2x. Oh no, wait, it'd be negative 10 because you have to multiply it, right?
Mm-hmm. Mm-hmm.
So it'd
And
be
not
negative
x,
10.
just negative
Yeah,
10.
just negative m to e. Right, yeah. And
To
then negative
the
2. Okay.
Yep, that's it.
Okay.
That's all there is to it. So 14, you can just do that in your head, right?
Yeah.
What would 14 be?
14. 4e is that negative? Yeah, 3x. Okay. Negative 12 e. Then up top is 3 at negative 3x.
Mm-hmm. Good. Now 15 is a little different, right? What do you do with
Yes.
the 3 out in front?
You have to multiply it by x, right? So
Well, what is the, no, you don't actually do that. So this is what I'm wondering if you know the rule for this. How do I take the derivative of 3? What's the derivative of 3? What's the derivative of a constant?
It's just crossed out, right?
Yeah, it's just nothing. It goes away.
Okay.
So that goes away. So the derivative of y would actually just be the derivative of this.
Okay. Negative.
Which is what?
Isn't it just negative e negative x?
Careful.
Oh
the
wait, because
it'd
be 1. Oh, it's gonna be positive.
Yeah, but it's still the negative in the
Positive.
exponent. Yeah.
Yeah.
Got it?
Yes.
And same with number 16, right? 16 is the same because the 2 doesn't matter. The number in front didn't have any impact on it.
Gotcha.
All right, how about number 17? What would the answer be for 17?
Negative 7 e.
Yep, negative 7 e to the x. Yep. In other words, it's itself.
Gotcha.
Right? Same with number 18. 18 is itself, basically. How about number 19?
19. Isn't it 1 over 4 e to the 2x?
Not 1 over 4, because you're multiplying 1/2 by 2. What do you get when you multiply 1/2 by 2?
Four over 2.
You understand what I'm saying?
Kind of.
So what's the derivative of 2x?
The derivative would be 2.
2. So you're multiplying 2 in the front. And what's 2 times 1/2?
Speed.
2 times 1/2 is just 1.
Gotcha.
Right? So your answer is just e to the 2x, because the 2 and the 1/2 cancel each other out.
Okay.
That makes sense?
Yes.
I'm going to duplicate this. Let's go to page 2. So I can, because I'm running out of room over here. because these other ones are a little bit more complicated. So how much derivative stuff have you done so far?
This is kind of like the start.
Oh, okay. So have you talked about the power, the power rule?
No,
You
like
you
I've
haven't.
heard of it, but we didn't talk about it yet.
So you don't know how to take the derivative of a polynomial?
No, not yet.
Okay. So that's pretty important. The derivative of, if your function is something like x to the n power, then the derivative is, here, let me write this to the right like I did on the last page. If your function is x to the n power, then the derivative with respect to x is n times x to the n minus 1 power. You bring the exponent down in front, and then you reduce it by 1.
Okay.
That's the power rule. It's like the main, in my mind, it's like the main derivative, the main way to take a derivative. So that's what we've been doing up to this point. What's the derivative of 2x? It's just 2. Because you would take 2x. So here's an example. If y equals 2 to the x, remember x is like x to the first power. Then the derivative of that, you take the 1 down and multiply it by whatever's there. And then you reduce this by 1. So it becomes 0, and x to the 0 is just nothing. I'm sorry, 1. X to the 0 is just 1. So the derivative of that is 2x. But if you had y, if you had y equals, let's say 5x to the third, then the derivative would be 15x squared.
Gotcha.
Okay, that's called the power rule. You take the power down, you multiply it by the coefficient, and you reduce the power by 1, and that's the derivative. Okay. So, and it's important to understand that for these next couple that we're doing. I actually thought you already knew that based upon the fact that you knew that the derivative of 3x is 3, but maybe you just only knew that. Maybe you only saw that 3, but that is what you're doing, that you're using the power rule. The derivative of 2x is just 2. But if it was something like this, that same rule applies. You take the exponent, you drop it down and multiply by the coefficient, and then you reduce the exponent by 1. So if your function was this, if your function was x cubed plus 3x squared, then your derivative, you can do it for each one of those. It would be 3x squared plus 6x.
Oh, because you have to multiply. Okay.
Do you see how I did that?
Yes.
So you're doing it to each one of them. Okay. So for number 21, this has what's called the product rule. Have you learned about the product rule yet? You probably haven't learned about that either.
No.
So trying to think of the best place for you to go to look for all these different things, but you probably should have, we probably should just have a list of all these rules, and you can go online and find, like, just do a Google search, like derivative rules for derivatives or something like that. Let me see if I can find it real quick, and I can show you one, because it's definitely something you want to have to be able to look back on. Derivative rules cheat sheet. Yeah, that's good. Let's call it derivative rules cheat sheet. Oh, here's a good one. See if it's, I'm going to be able to okay, let's see if I can import that into, all right, I got ourselves a nice little cheat sheet here. Do you see one too? Are you looking
I don't
one
see
up?
anything. Oh. Let me look one up.
Here, I'll put it on here. I just have to open this up on my computer so that I can insert, because from my iPad it's not as easy to do. Okay, here it is. So here's my derivative rules cheat sheet. This will hold us off for a little while, I think. Actually, this isn't really a lot of them, but this is 3 of the main ones, and it's one of them that we need for right now. It's called the product rule. So the product rule, product means multiplying, right? So if your function is, if your function, your y is a product of 2 functions, then the derivative of y is equal to the derivative of the first function. See how that's the derivative of the first? You understand what that notation means?
Yep.
Okay. It's the derivative of the first function times the second function plus the first function, f of x, times the derivative of the second function. So here's an example. See how this is 2 functions, it's x to the 4th, and then it's sine of x?
Yep.
So the x, look, what they're doing is they're kind of doing the work over here. F of x is x to the 4th, and the derivative, notice that's the power rule, is 4x to the 3rd. And if g of x is sine x, the derivative of sine x is cosine x. That's just something you have to kind of memorize. Have you learned that yet?
No.
Now you know. So this is the kind of thing where you just have to kind of, as you go, you kind of write down the stuff that you're learning so you can refer back to it. I could spend time explaining why the derivatives are these things, but you don't really need to know why. You just need to know how to apply them when you get them. Okay.
Yep.
So then the derivative of y would be equal to, look at how this is the derivative of f of x times g of x plus f of x, see how that's f of x, times the derivative of g of x. So there's your answer. That is the derivative of y. What's the derivative of this function? It's that right there. Okay.
Yep.
So here's another example. Here's your first function. Here's your second function, natural log. By the way, the derivative of the natural log of x is just 1 over x. Again, this is just one of those things you have to memorize. So just plug in the different things. Here's the derivative of x. Here's g of x. I'm sorry, the derivative of f of x. Here's g of x. Here's f of x. Here's the derivative of g of x. And then you simplify it and you get that, because this x cancels with one of those x's there. So this just is 2x here. Okay, so that's called the product rule. Now there's also the quotient rule and the chain rule, which we may be doing in a second as well. But let's go back to your problem now, and let's take a look at what you have on number 21. So do you understand why I had to teach you the product rule for number 21?
Yes, because you're gonna apply it for.
Yeah, because you have a product, right? Your function is x to the 4th times e to the x. So there's actually two, it's a product of 2 functions, right? So
yeah.
let's call this, I'm going to color code this for you. Let's call this f of x. So f of x equals x to the 4th, and the derivative of f of x is 4x squared, or cubed, sorry. Follow that?
Yes.
And let's call this the black, or the e to the x, let's call that g of x. What's the derivative of e to the x?
So I have to put them all together. So like x.
Do you remember tell me what the derivative of e to the x is first? You remember what that is?
To the e to the isn't it just, it's e.
You got it. It's e to the x.
Yeah.
Yeah, good. So let's put them together. So what's the derivative? Do this in red. What's the derivative of y? You take the derivative of f of x, multiply it by g of x, and then plus, now you take f of x and multiply it by the derivative of g of x. And that's your answer.
Okay. That doesn't seem too bad.
It's really not that bad. So let's try number 22.
Okay.
So y equals x to the fifth times e to the x. So what would the derivative? Let's just do it. Let's not show the work. Let's just do it in our head. What's the derivative of x to the fifth?
X to the fifth. It would be 5x to the fourth.
Good. Now what am I going to multiply that by?
By ex.
And then what?
And then you're gonna plus.
Good.
The x to the fifth. Then plus. No, then it's gonna be the e to the x.
Perfect.
Okay.
Nicely done. All right, so number 23 is a little bit trickier, but really not. It's the same concept. So what do I do for 23?
Would you? So would you split it? You'd split it up of.
Yeah. So the key here, it's just the same thing, but now you're just going to take what's the derivative of this first function?
It's going to be 2. Is it 2x to the plus 3?
2x plus 3. Good job.
Yeah, the 9 cancels out.
Yeah.
And then times the ex. Plus the x squared plus 3x minus 9. And then ex.
Good. Now we can actually simplify this some more. Can you see why? If I distribute, there's going to be like terms. If I distribute the e to the x in here, you'll see there's going to be some like terms. So we've got x squared e to the x, we've got plus 3x e to the x, and minus 9 e to the x. So I can add together, see how I've got 3 e to the x minus 9 e to the x? That's a total of negative 6 e to the x. And see how I have 2x e to the x and 3x e to the x? That's a total of 5x e to the x, because they're the same. They're the same variables. You understand what I mean by that?
Yes.
And then, of course, I still have this thing, which doesn't have a like term, just x squared e to the x. And in fact, what you can do now is you can factor out that e to the x, and that usually is what will look nicer. So if I factor that e to the x out, I will just get x squared plus 5x minus 6. And the reason that's nicer is because then you actually are eventually going to want to factor this even. Not that you need to do this for this problem, but you're probably going to want to write x plus 6 and x minus 1. And I'm just kind of giving you a little foreshadowing. The reason that you want to do that is, do you remember how it's really important? It's really valuable to know where your zeros are when you're finding things, your x-intercepts.
Oh, yep.
And that's exactly what you want. When you're taking derivatives, you want to know what the x-intercepts are. Because the zeros of the derivatives, the x-intercepts of the derivatives are where the original function had maximum and minimum values. And that's really kind of one of the main points of calculus, at least the one you're doing, is finding where you maximize and minimize values. So let me just take a pause right here. Can I show you what I'm talking about on a graphing calculator? So, and you might not understand this. Maybe your teacher has talked about it, maybe she hasn't, but if you can, see, how do I do the y equals on here? Y equals, so I'm going to punch in that what we just did there, which was what? X squared plus 3x minus 9. Is that the one we just did?
Yes.
X squared plus 3x minus 9. So there's that. And then times e to the x. So let's see, where's e to the x functions?
Is it ln or couldn't that be?
Well, it's the inverse of ln.
Oh, true.
Maybe it's sitting here already. I don't see it. I mean, it's definitely one of the most important functions, so it should be here somewhere. Is it exponent? No, it's not exponent. Maybe it's. Did I just write e to the x? GCD join shuffle mod. Let's see, could I shift maybe? No, I don't have shift. It's weird that I don't have an E in here anywhere.
Yeah.
ABC, maybe? Do I go ABC? Do I just do E
Oh,
to
there's
the
an
X?
E right there.
Yeah, I wonder if I just do that. E to the X. It's just weird that I don't have those, but yeah, maybe that's all I'm supposed to do. Where's X? Yeah, there it is. Yeah, I guess that's how I do it. Okay, so there's my function. And you can see, do you remember what I talked about before? What I talked about the value of those
You can
points
see the
are?
min and max
Yeah,
values.
do you see what one of your minimums is? Do you see how it's this
The
right
min-
here?
Yeah.
You
Like,
see how it's at 1? The
yep.
minimum is at 1, or well, at least one of them that we can see is at 1. And look at my derivative. Look at the derivative function.
Oh, I see.
What one of the zeros is at 1?
Hmm.
Do you see that?
Yes.
Do you see how one of my zeros is at 1? Is at x equals 1? The other one is at x equals -6. Let's see what happens if we go to -6. Now, sometimes, so it is. See how there's a maximum
0.
at
Yeah.
there's a maximum. It's not a 0, it's a maximum actually. That's actually going to be a maximum. It's kind of hard to tell, but if I zoomed really tight in on that, you would see that that point is taller than all the other points, is higher than all the other points. That's a maximum, and +1 is a minimum. And that's one of the major things that we do when we're trying to learn how to find derivatives of functions. So in the real world, what's this calculus for again? For business or for what?
Life sciences.
For life sciences. So perfect. So when you're taking, like, let's say you're looking at, oh, I don't know, the population of crickets versus frogs. I don't know, just making something up, in an area. Well, you have all this data, and you take this data and you use the data to find formulas or equations. And the equations, when you learn how to, calculus allows you how to calculate different things based upon that data. That's what calculus does. That's what you're doing with calculus in short. And so taking derivatives is really nice, because what the derivative shows, so here's my function. This purple graph here is the function graph, but the derivative graph tells me the max and min points on my function. That's what it does for me. So it's kind of a shortcut. It's like a hack on figuring out what some important data points are from your original function. Does that make sense?
Yes.
So again, I'm not going to go into it any more than that, but that's one of the kind of the motivation behind what we're doing here. So for this, so that's the answer. So for this number 25, remember what I told you? What's the derivative of sine?
Isn't it cosine?
Yeah, it's cosine. And the derivative of cosine is negative sine.
Yep.
Is that right? Or is
Negative.
that vice versa? I actually kind of don't remember.
I think that's vice versa. You're right. So I remember.
I believe that's right. I believe that's correct. Here, let me look for another. Yeah, the derivative of sine. Yeah, here's another good derivative rule. Oh, here, I'll put this one on here too. Ooh, Google Lens, how does that work? I just clicked on the button on Google and it's save as. Oh, there you go. Derivative rule cheat sheet. I'm saving it to the desktop. Okay. Oh no, I didn't want to do that. I want to save it as a. Oh, it's not letting me save it as. Sorry, I'm talking to myself because I'm trying to.
It's all good.
I'm trying to save this thing in a different way here. I'll just save it the way I know how to save it on my. Okay, derivative rules. So I'm going to put this on here too, so you can jump back to this Jamboard, and you can take a look at these. And of course, you can find these yourself. This is going to be on page. Let me add a new page to. It'll be a page 4. I'm not on it right now on Zoom, but I will be shortly. I'm trying to print it or paste it. Okay, page 4 now. That's not what I thought I put on there. Let me try that again. Apparently I took 2. Oh yeah, there it is. So here's your derivative cheat sheet. See what I was talking about before? There's the derivative of e to the x. It's just e to the x.
Yes.
Here's trig ones. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cosecant is negative cosecant cotangent, etc. And again, what does this mean? Well, here's what it means. It means if I take my function, again, I'm kind of going a little bit more into this now so you understand some motivation behind this, because this is undoubtedly where you're going to go at some point in this class. And it sounds like maybe your teacher's not really teaching you this. So if I have sine of x, what did I say was the derivative of sine x?
Cosine.
Mm-hmm. So if I graph cosine next to it, guess what's going to happen guess what these two things are going to help me see when I graph them with each other? Do you see every time I get to a peak on here's my sine graph, the black one is my sine graph. Every time I'm at a peak, where is the cosine graph at?
It's the same.
It's not the same. Every time I go to the peak, there's the peak on the sine graph. What do you notice about that same value, that same x value on the cosine graph? Where is it?
It's 1 over.
No, it's 0.
0.
Look, can you see what I'm pointing to?
Yes.
That point is pi over 2 comma 1. That's the sine. The sine of pi over 2 is 1. Well, what's the cosine of pi over 2?
It's 0.
It's 0. And the reason, and so remember what I told you? The derivative, what's the derivative of this black graph? What's the derivative of that black function? What's the derivative of sine of x?
Cosine.
It's cosine of x. So if I solve where the cosine is equal to 0, what is the derivative, setting the derivative equal to 0, going to do for me? What's it going to help me find out about the original function?
That's going to be 0?
No, it's where the original function has a max or a min.
Okay.
I'm going to say it again because I know that's kind of confusing. You're just trying to wrap your head around it. Yep. This black graph is my y function, y equals sine of x. The derivative of sine of x is cosine of x, which is this red function. One of the main reasons we want to find derivatives is because derivatives, solving the derivative for 0, finding out where the x-intercepts of the derivative are, help us know where the max and min points of the original function are. So every one of these red functions, every one of those red zeros that I get there is going to correspond to either a max point or a midpoint on my original function. That make sense?
Yes.
So that's kind of the motive. That is actually one of the main points of calculus that I want to make sure you understand. So we can get it gets very tedious when you're doing all these calculations and stuff, but that's kind of the main idea behind calculus, is that it's going to help us find max and min points of the original function. Okay.
Gotcha.
All right. So are we good with that first page, or do you want to keep working through some of it?
I think we're good. Now I understand.
Okay, because actually number 27 and 28 are quotients. Do you need to do 27 and 28, or do you not have to do those yet?
No, I actually know how to do quotient.
Okay, because the quotient rule is on here, but if you don't have to do it, let's just skip it for now. Maybe we'll come back to it if we have time. So your next exercise set is actually not about derivatives, it's about logarithms.
Mm-hmm.
So again, we have to kind of have a basic ground rule of logarithms and understand what a logarithm is. Do you remember logarithms? Do you understand what a logarithm is?
No, not really. We just started derivatives and logs at the same time.
Okay. So the thing about logarithms is you would have done this in algebra 2 trig and in pre-calculus both. But those last couple of years for you have been COVID abbreviated. So I wonder how much you really understand or remember about them. Do you remember logs?
I do not.
Okay, so a logarithm is basically the inverse function of an exponential equation. So if my exponential, let me give you an example. If I said that y equals 3 to the x, that's an exponential, right?
Mm-hmm.
You can actually write that as a logarithm. And the way you write it is you use the equivalence. You write log base 3 of y equals x. Those are the exact same equation. One is solved for y and one is solved for x. They're inverses of each other. Okay. Another way to think about it is, if I said log base 3 of 9, that's going to equal 2. The log base 3 of 9 equals 2. Here, let me write it over on the log side. The log base 3 of 9 equals 2. You might be going, well, how do you know that? Well, I know that because what logarithm means is, 3 to what power equals that number. That's what a logarithm is. It's 3 to what power equals that number. So 3 to the second equals 9. I knew that 3 to the second equals 9. And I understand how logarithms work. So I knew if I said, hey, what's 3 to the second? What would you say?
3 to the second?
Yeah, if I said you'd say 9. If I said, hey, what's log base 3 of 9? You probably wouldn't know what to say because you don't ever deal with that. But I'm telling you, the way to deal with it is you ask yourself, oh, well, that just means 3 to what power equals this.
Okay.
So you'd say, oh, it's 2. Okay, that's logarithms. That's what a logarithm is. That's kind of the definition of a logarithm. Now there's properties that go along with logarithms as well. So here's some properties. And I could probably very easily just take a picture online somewhere, but I'll just write them out for you. So some properties of logarithms. If you have the log base b of something to the n power, let's say, you can take that n, that exponent, and bring it down and make it a factor. That's one property. You can take that n and drop it down to the front. Okay, that's one of your properties. Another property is log base b of a plus log base b. Oh shoot, that's a bad. I shouldn't be using A's here. I should use X's. Let me change all these A's to X's. So I'm gonna run into some problems. Log base b of x plus log base b of y equals the log base b of x times y. That's another property. Another property is the log base b of x minus the log base b of y equals the log base b of x over y. Another property is the log base b of itself is just 1. But that kind of follows from the definition. You probably could figure that one on your own. I'm trying to think of what other properties of logs there could be. Well, I'll think of them when I start trying to do the problems. But these are called, I'm basically just taught you like 2 weeks of a review of logarithms from high school.
Gotcha.
So how do we do them? Well, it says write an equivalent. This first one, write an equivalent exponential expression. That's this. You just use that little formula there. So the equivalent for this would be 2 to the 3 equals 8. Got it?
Yes.
2 to the 3 equals 8. So how about number 2? What would I write for number 2?
Isn't that just 1? Wait, no.
Number 2 is to the right over there. What would I do for number 2?
Isn't it, you said 2 to.
So look at the little trick here that look back to the right again. What do you do to go from here from log to exponent? You start at the base and you go to the right. 3 to the x equals y.
Oh, so 3 to the 4th equals 81.
3 to the 4 equals 81. Perfect. How about number 3?
Uh, 8 to the 1/3 equals 2.
How about number 4?
27 1/3 up to the 1/3 equals 3.
Yep. So for number 5, it would be a to the j equals k.
Yep.
Right? You get how that works? And let's just do
Yes.
number 8. What would number 8 be? Now remember that one trick I told you.
Okay.
What do you do first? Or look at the first property.
The first part. Okay. So
Where can this -1 go? You see, if I went this direction with this equation, where can this number in front go? Do you see where it's going?
exponent. So would it be -1? Like
yeah, then so -1 would go up to here, and now write it.
So then it would be b to the -1.
Nope.
Is w.
Nope. B to the w. B to the w equals v to the -1.
Oh, v.
See, you first put this -1 up here. You first put the -1 up with above the v. You see what I did?
Yes.
That's how you do that one. Okay, so now the next section says write an equivalent log equation. So now what am I going to do? Instead of going from here to there, I go from exponent
to log.
So what's the log? It's log
e
base e of
is it b equals m.
Perfect. So here's what you'll hear people say: a logarithm is an exponent. Do you see how m is an exponent?
Yes.
And that's my logarithm. That's why they say that a logarithm is an exponent, because that my exponent is m, but I'm rewriting it as a logarithm, which means the exponent is actually the logarithm. Does
Gotcha.
that make sense?
Yes.
So like, what's the exponent of, look at number 1 again. What was the exponent in this expression?
3.
It was 3. And see how 3 is my logarithm?
Yes.
The log base 2 of 8 is 3. That's what they mean when they say a logarithm is an exponent. You'll hear that a lot, maybe. So continuing, this would be log, and the base is always the base. The base of the exponent, look over to the right, the base of the exponent is the base of the log. See how those are both the base?
Yes.
So remember, the base is the base. So it's log base 10 of 100 equals 2.
Gotcha. That makes sense.
Okay, got it?
Yep.
So this one over here, number 14, would be the log base 10 of 0.01 equals -2,
2.
etc. Okay. The next section is talking about finding values given logarithms, and this is what's going to use these other properties that I wrote at the bottom over there. You see those properties I wrote at the bottom?
Yes.
So the log base b of 15, well, the log base b of 15 is the same as, I'm going to write this to the right. The log base b of 15 is the same as the log base b of 3 times 5. And what do we know about 3 times 5?
Equals 15.
3 and 5 equal 15, but how can I rewrite this instead? Look at what I did. I can break it up as a sum.
Okay.
So this equals the log base b of 3 plus the log base b of 5.
Okay.
And I know what the log base b of 3 is because they told us that. It's 1.099. And I know what the log base b of 5 is. They told us 1.609. So add them together, and that will be your answer. 2.7 something. It's 1.099 plus 1.609, whatever that is. Punch it in your calculator. I'm trying to do it in my head, and it's 1.708. I don't know.
Yep.
Is that right? 1.708?
Yep.
Okay. Do you see how that worked?
Yes.
So number 20, let's try number 20. That looks fun. I think you can do number 18, right? It's just going to be subtracting them instead of adding them, right?
Yes.
And then, well, 19 is kind of tricky because it's log base. Oh, this is another property. The log base b of 1 equals 0. That's a good property to know. And that's because b to the 0, anything to the 0, what does anything to the 0 equal?
1.
It equals 1. And so this is saying that, but as a logarithm. So when you see this right here, number 19, when you see the 1, this is going to be log base b of 1 minus log base b of 5. And the log base b of 1 is just 0, because anything to the 0 equals 1. So this is just negative log base b of 5, which would equal negative 1.609. Okay, and don't forget the log base b of itself is always just 1. So when you see something like this, you're just like, oh, well, that b doesn't really, that's just going to be plus 1. You're just going to be adding 1 to it. So it's the same property here. You'll use this kind of thing, but then you're going to have log base b of b, which is just 1. So you're just adding 1 to whatever that other one is. Am I going too fast? Or you understand what I mean?
Oh no, I'm understanding.
Good.
I'm trying to remember everything from high school.
Right. It was like I said, you're at a disadvantage because of COVID. It kind of shortened these important. You probably didn't have as much practice with these. So let's do number 20. So number 20, remember the square root is like the 1/2 power, right? So this is
Yes.
like saying the log base b of b to the 3/2 power. You follow that? Or do I have to show you that? This is more exponent stuff. Here, let me write this up here. Log base b of the square root of b cubed. The square root of b cubed. This is like saying the log base b of b cubed to the 1/2 power, because that's what a square root is. And what do you do with powers when you raise a power to a power? What do you do?
They add them. No, you multiply them.
Yeah, you multiply them. So that's how I got 3/2.
Gotcha.
Now, what's the property? Look at the property we can apply here. What does it say if you have a log of something with a power exponent in it? What can you do with that exponent?
Oh, okay.
Do you see it?
Would it be, yeah, would it be 3/2
Mm-hmm.
times log b over b? Yeah.
That log b of b. And what's the log base b of b?
The log base b, isn't it 1? It's 1, right?
It's 1. That's right. So this just equals 3/2. Okay.
Gotcha.
Same with the next section. You're using this without using the calculator. So 20 is 4 times 5, right?
Yes.
So you're just thinking of it like that. And remember, ln means log base e. So what's the ln of e equal to?
4 times 5.
No, just the ln of e.
Oh,
What's the natural log of just e? If that, you know that natural log means log base e. So what's the log base e of e?
Isn't it 1 too?
Yeah, it's just 1. Because e to the first power equals e. Okay. No, ln of 100, that one looks a little bit trickier. You have to try to think of a way to write 100 in terms of 5 and 4. Oh, I got it. It's 5 times 5 times 4, right?
Which gives you 20, then 20 times 5 is 100.
Don't do 20. Just do this. Do ln of 5 times 5. Do ln of 5 squared times 4. And then break it up using this property over here. So that equals the natural log of 5 squared plus the natural log of 4. Right?
Yes.
You follow what I'm doing there? And then what can I do with this 2?
Bring it in front.
Bring it in front. So this equals 2 times the natural log of 5 plus the natural log of 4. And now you can plug in your numbers, plug in your values, your 1.6094 and then just do it by hand. Okay.
Yep.
We got through it all. Got 5 minutes left. What else? What else do you have? What other questions do you have? Are there other things that you're struggling with?
No, it's just understanding logs and trying to remember everything back from high school.
Right.
And then, yeah, I don't have any questions. I just need to brush back up on the derivative rules too.
Yeah. What class did you take? Did you take calculus in high school or no?
I took pre-cal, but like we were all online, so I felt like I really didn't learn anything.
Yeah.
And right now, I got a high score on like the placement exam, so that's why they put me in calculus. And then I just did not get a really good teacher because it's not just
Mm,
me that's struggling with the class, it's actually the whole class.
mm.
Yeah.
Well, you should probably direct your classmates once you see this video, once it's posted, the live video, you should maybe direct it to your classmates, and maybe you guys can kind of together, um, buy a cup, buy an hour together, like get other people to pitch in, and then we could have 3 or 4 people on here if you have some friends that need some help and they're in your class.
Oh,
That'll make it cheaper
exactly.
and a little bit easier.
Thank you. Yeah, that
Okay.
might help.
Yeah, and then we can just do like even a Sunday night session for, that probably works well for college kids. My
Yes.
daughter's in college and she's always calling me on Sunday night asking me for help. So unfortunately she's in Arizona, so whenever she does, it's always early for her but late for me, and I'm like, you got to call me earlier than this. So anyway, all right. Any other questions?